S. So don't forget about those little S's in your notes. So this is a gas phase concentration, which I can relate to pressure. And then again, we have this average gas velocity, which is there.
Where's the 4? Are you dividing by 4?
Yeah, it's...
Is this an empirical formula?
They should read about that.
No. It's not something that we're going to get into in this class, but there, it comes from...
It's not for the maximum distribution of velocity. Right?
No. It comes from... I'm trying to think of the best way to explain it. Yes. That's a better way of putting it. But no, I mean, I don't think that we're going to get into kinetic theory of gases. So let's... Because we're gonna kind of abandon this form here in a few minutes. So you're seeing a little bit of where the final form is coming from, but we don't want to start all the way from scratch. So the pressure of A, U over 4. So, if I do these notes again, let's start here, because I think this makes so much more sense to you guys. And then we'll talk about what is K. Because K is where all the questions you have are coming from. And we're just not going to get into it, so it's kind of silly to talk about it. But no, this is a lowercase k. I mean, I've been doing that much the whole time, right? The little flag. Okay, so it's a rate of a reaction. So what is the reaction? A plus star goes to A star. All right, so you guys have done this. How do I write an elementary rate law for that reaction? R is equal to K times the concentration of what? A times the concentration of what? Star. Okay, let's look at what we have. Concentration of vacancies, pressure, which you guys know is related to the concentration, and a rate constant. This rate constant, though, is not like the rate constants we've used previously. It doesn't come from the same physical background. It comes from this, which again, this is a sticking coefficient, which is essentially saying if I bombard a molecule with a surface, what is the probability with which it will stick to that surface? 0 to 1. Yeah?
Is it more or less simply the steric coefficient on the pre-exponential factor?
It's related to it. Yeah, I mean, they've come from similar. You can derive a pre-exponential factor from a very similar background. But no, I mean, so really all of this was so that you had some understanding of where K comes from. It comes from the velocity of the gas hitting the surface, right? If it's moving too fast, it can bounce right off. It comes from the concentration of the number of sites. And it comes, you know, the gas constant, the things left over from the ideal gas law are just because we put it in terms of pressure instead of concentration. Yeah?
The rate of absorption is d what dt? Is it dA dt or dA star dt? What is it? Is there a negative there?
The rate of oh, I see what you're saying. No, the rate of adsorption is dA star dt. This is not the rate of consumption of A. This is the rate of adsorption. So that's why we left off the negatives. But that's a good point. Normally we would write that with a negative because we would write the rate of consumption. Yeah?
The rate A at the very top of that board.
Yeah, this one.
How did we get there? Because that just looks like phi.
I put it down wrong. Yeah, you plug phi into... Oh, sorry, I left something off. I misread his notes here. I read SO, and in my hurriness, I thought it was the word so. So, and I'm like, that does not make any sense, but I don't see sticking coefficient a lot, so I just rolled with it. This is equal to this. This is all one line. That makes sense now? Yeah, sorry about that. So some units, again, this is the form we care about. Try to forget everything you just saw about kinetic theory of gases. It's something that you would get in a grad kinetics course in more than 15 minutes. So the units here, moles per second, grams catalyst. You say,
Do they
huh?
teach that here? Do they have that in class?
I'm teaching it in, yeah, as soon as I'm done with you guys.
That's great.
It's going to be offered 600 code, so if you're 500 code or whatever, so you guys can take it if you want.
Is it for technical elective? Yeah.
Wait, say that again?
Technical elective.
I presume, yeah, it's a chemical engineering course, it's a grad level chemistry course. If that's not a technical elective, I don't know what is. Yeah.
Well, we already like mass basis and like continuum and stuff like that to take graduate kinetics.
I don't understand what you're asking. Those are fall courses. This is a spring course.
Like when people can keep up with the math without those without that background.
Oh, yeah, absolutely.
Is it easier than this?
I wouldn't think so.
Are you writing your own notes or using somebody else?
I'm using Jason Weaver's notes. You have to be used to it by now. If you're interested in grad school, it's something to think about taking. I took a grad course when I was in undergrad. They do not count. When you go to grad school, you have to take it again. But I took a transport course out of Dean, which is the same book they use here. And if I hadn't taken it once before, I might not have got through it the first time. So it can be very useful to take a course as an undergrad that's a grad course. You usually get graded pretty nicely. And
The grading is nicer?
you usually grade the undergrads nicely. Like I know when I took it, I got destroyed by every exam and I got a B in the course. I think he was being generous. No, understand, and I think that's probably common here too. I mean, you'd have to ask Adam.
I hope.
You hope.
I don't know, it's Dr. Butler, so.
Good luck. All right, so here are the units, just so we don't get too sidetracked. So this is mole of adsorbed species, right? So in this case, like mole of A per second. So this is again a rate of adsorption. Normalized now per gram catalyst. So we've talked about this previously when we talked about PBRs, that rates are now often normalized per gram catalyst. There is another normalization that often happens that we might talk about, where you would normalize it per gram surface. Or you could do per mole surface, right? You could do moles instead of grams. But essentially what you're describing there is the amount of atoms or moles of atoms on the surface of the catalyst instead of in the total material. Yeah?
Is the RA up there the same as R absorption?
Yes.
Okay.
Yeah. Yeah, he just left it off in some places and I didn't write it back in.
Okay.
So the rate constant, we've got 1/2 times inverse pressure, because we're using pressure here. And then the concentration of vacant sites is in moles of vacancies, which again, you can have moles of anything. Moles is just a way of counting. It has nothing to do with chemistry. So moles of something per, in this case vacancies, per gram catalyst. All right, so some assumptions that are in this model, which are extremely important, so don't forget. The probability of sticking at a filled site is 0. So essentially, I cannot adsorb to a site that already has an adsorbate. That's an assumption. Yeah.
Can take a dynamic equilibrium study where you hit it, the other one leaves, and that's okay?
That's okay. In reality, there are sites that can uptake more than one species. Sometimes you would just add a site to your site balance, but sometimes it's not so clear what you do. So again, these are all assumptions, every single one of which is flat wrong. But somehow it works like magic. Second assumption, And this one really, I don't want to say the phrase because I never understood it, but this one really bothers me. Anybody know what "gets my goat" means? Because I don't know what it means.
Grinds my gears, what bothers you?
Grinds my gears, I understand. Bothers me, I certainly understand. I never understood the phrase "gets my goat." But what really does that?
You never met a goat?
That might be the problem.
They're assholes.
Maybe your goat's your pet peeve.
Yeah, I don't know what pet peeve means either. I know what the phrase means. I'm saying I don't know where it comes from. Interactions between adsorbates does not affect future adsorbates. So for example, if I have my grid that I erase and it's covered in A and I've only got one site left, that site, according to this theory, is the exact same as if the surface was completely empty.
So it's not cooperative? Is that what it's called?
Or repulsive. The point is that the coadsorbed species do not interact with one another at all. Yeah?
Those are already built into the kinetic theory. The acid where it's derived from because it's knowing about the forces and
Yes, it's from where it's derived. Yes. The assumptions of the model have to do with where it's derived. But you could include terms that represent the coadsorption interaction. And I mean, I've tried to. Yes?
So this implies that the S naught sticking factor,
Yep.
whatever, is always constant?
Yes.
Or, so it's not even a function of theta?
It's not a function of coverage, no.
It's gotta be a function for certain molecules, right?
Different molecules would have a different sticking coefficient, yes. But the point is that if I just have A filling up a surface, that process only depends upon the number of empty sites and the sticking coefficient. And the sticking coefficient is independent of the number of empty sites. The reason why Adam's finding this tough to swallow is he's done this with DFT, and that's just wrong. Most adsorbates take up a little bit more space than they have on a surface at one monolayer, and so they push against each other. They don't want to be right next to each other. CO being a prime example. Yeah.
What about variations with temperature and pressure?
That shows up. It shows up in the sticking coefficient, and it shows up in. It probably shows up in the sticking probability, but I'd have to go back and look at it. But it shows up in K. There was a temperature dependence in K.
And it would show up in the average velocity.
Yeah, that's the other place it's going to show up.